Lesson 3 introduces the I/O window. The embedded system that we will create implements a simple NOT gate with the input on port T bit 1 and the output on port T bit 0. In particular, we will edit, assemble, and simulate a 6812 system which inputs from a switch, complements the value and outputs to an LED. In the previous two lessons, we created a program file, one of these, for the source code, and a microcomputer file, a .uc, for the information inside the microcomputer. However, electrical and mechanical devices that exist outside the single-chip microcomputer will be defined in an I/O file. In this example, we will connect a switch and for the input and an LED for the output. As we can see, there are three files, and they are linked because the first part of the file, the first part of the name, all begin with lesson 3, and they are saved in the same folder. Together, these three components, the software, the microcomputer, and the external hardware, combine to create an embedded system. Okay, let's begin. We will first begin by attaching devices to the I/O window. So to attach a device, in this case we want a switch, we click on the I/O window, and then we execute a command in the I/O menu. So if we want a switch, we execute I/O switch. In this position, we type the pin that we want to connect the switch to. I'm going to connect it to port T bit 1. Notice when I finish the name of the port that the lowercase letters I typed jump to uppercase. Let's try that again. I delete it. If I tried to connect it to port Q bit 1, notice that the PQ are still lowercase. Because there's no port Q on the 6812, this is telling me there's an error. Let's fix it. So notice when I hit the 1 that it jumps up to uppercase. I can specify the color, and I can also give it a name, a label. So I've just added a switch into my system. And I also need an LED, and I do a similar thing. I'm going to put the LED on port T bit 0. Notice it punches up to uppercase, and I'm going to give it a color. I like green, and I'll give it a label called out. So I've connected my two external devices, a switch on port T bit 1 and an LED on the output. Okay, now let's program my system. Okay, so my program goes here in the RTF file. So I type it in, lesson 3, it's a comment. I'm going to use a label, a symbol definition, for the port names to make my program more readable. Port T on the 9S12 exists at location 240, that's hexadecimal. And the direction register for port T exists at location 242. Okay, so I'll define them. That'll make it easier for my program to be readable. Okay. I have no variables in this case, so I'll begin by defining my program here in ROM. And ROM on the 9S12 exists at 4000. And I'll begin at labeled main. The first thing I'm going to do is set the direction register. Now a value of 1 in the direction register specifies that pin is an output, and the value 0 specifies input. So this number, which is in binary 000, 0001, means that bits 7 through 1 will be inputs, and bit 0 will be an output. Exactly what I want. And I got to store that value into the direction register of port T. And I just do this once at the beginning of my program, and this will initialize port T. Bit 0 is an output, and bit 1 is an input. There we go. The main loop of my program will perform the NOT function. I'll begin by reading the value from port T, and this will bring all 8 bits into the accumulator. And in particular, the value of the switch that I'm interested in will show up in bit 1, because that's where I connected it. Next, I'm going to complement that value. I'm going to flip the bit 0 to a 1, 1 to a 0 by exclusive ORing it, and this will flip bit 1. The next thing I got to do is shift the information down into a position bit 0 where my output is. So I'll logically shift it right. I'm going to shift the accumulator, and that'll move the information down into bit 0. And the last thing I'll do is I'll store that result back out to port T. Those 4 instructions executed, now they have to be executed over and over again. So I'll create an infinite loop, branch loop. There's no stop instruction in this case, so these 4 instructions will be executed over and over again, performing my not function. Update LED. The last thing I got to do to my program, as you know, all computers need to know where to start, and on the 9S12, there's a reset vector at FFFE, which contains a 16-bit address, which will tell the computer where to start. Okay, I've typed my program in. The next thing I have to do is assemble it. Assembling converts the source code to object code. It's loaded into ROM, and there's my listing file down here. When I execute it, I'm going to be interested in register A, and I'm going to look at register A as an 8-bit hexadecimal. Enter. And I'm also interested in port T as a 8-bit hexadecimal. And so these are the 2 pieces of information I want to debug. As I execute, and I'll execute this 1 instruction at a time, we see that the first 2 instructions will specify that port T bit 0 is an output and port T bit 1 is an input. Okay, so those are done once. The next instruction, the load A, will bring into the accumulator the current contents of port T. Because the switch is not pressed, that value is a 0. The exclusive OR instruction modifies bit 1, 0 went to a 1. So we see register A has got bit 1 set. And then it's shifted over. The bit 1 gets moved into the bit 0 location, and then the value of that is written out to the port. The output bit in port T bit 0 is set. We see 5 volts on the input, and the LED turns green, just as I want. If I were to run this continuously, this program executes those 5 instructions, load A, exclusive OR, shift, write, store A, branch, those over and over again, and I interact with an I/O function by, if I want to switch the change, I click it. You notice the switch changes, it's set, and my NOT gate flips the LED. And so the light, the switch is pressed, the light is off, the switch is not pressed, the light is on, and it works. So in this lesson, the objective was to introduce the I/O window. So as a conclusion to this example, let's look at what some of the other options would have been if I wanted more or different I/O. So I'll make this window bigger, make it totally big, and then I'll add some more devices that we don't need, but they're kind of curious for us to see. Okay. If I wanted a CRT terminal, I could attach it to the serial port. That's port S on the 9S12, and specify the baud rate. And so this command will add a serial port and create a new window. See, the I/O port is shown here with the CRT terminal tied to port S, but it also introduces another window, the CRT.RTF. It is into this window that our external terminal you will interact with. Anyway, let's add some more devices. That was a CRT. Let's add a simple liquid crystal display. We'll tie 4 bits to PA, port A, bit 4, 5, 6, and 7. That's how you specify that. And we'll tie another 4 bits to port A, bit 0, 1, 2, and 3, and I'll give it a name. This will be my liquid crystal display. And so 8 bits of port A are tied to a 2-digit, simple, parallel interface liquid crystal display. Okay, we can add an analog device, and that'll obviously be connected to the A to D converter, which is port PAD on the 9S12. We can specify the shape of it, like we want an electrocardiogram. We can specify the amplitude of the electrocardiogram, the period, and we can even add noise. And that shows up as an analog signal that our A to D converter can sense. We can add a keyboard. And a keyboard, this is a matrix keyboard, so we need 8 bits to do a 4x4, and we'll put it on port B. Okay, port B7, PB6, PB5, PB4, PB3, 4 rows, 4 columns, PB2, PB1, PB0. We can specify the keys that get pressed. We can specify switch bounce if I wanted. But there's my port. Again, to interact with it, you click on the buttons as you need to. Okay, let's add. We can add a DC driven DC motor with a 1 port, which is the DDA converter. Say PB0. We could add the A to D, the tachometer, to PAD1. We can specify the parameters of that DC motor, and that adds us a DC motor shown here. Let's see. We can add an infrared remote controller. We'll tie it to say PT2, and we have to specify the pins on the buttons on the remote control, and all of the codes that get sent when those buttons are pressed. Lots more information on this one is in the help file. Okay, so again, to send a remote control, you click on it. Okay, let's see, what else can we add? We can have an Hitachi 44780 control liquid crystal display. It's either and specify the size of that display, 4-bit mode, 8-bit mode, choose a label. Skip that one. We can even add a remote control car. It's a stepper motor car with 2 stepper motors to drive the back wheels. It's lots of slot sensors and wheel sensors and track sensors, and GPS, and all sorts of parameters that you can specify for this remote control car. So in summary, we've introduced the I/O window. And in the I/O menu, it specifies the various kinds of devices that you can attach to the I/O of the microcontroller. So to quit, we exit, and as it goes out, we will save it, because next time we can come up and pick up where we left off. Well, thank you very much, and that's it.